electrical needs or uses with batteries and fossil fuels, lots of ways that they're used. So real quick yesterday, I want to go back. When you're thinking of a chemical reaction, it has a bond, right? And so during that chemical reaction, the molecules or the atoms are going to possibly rearrange, like split and rearrange. It's that splitting and rearranging that can release energy, right? And the videos obviously showed that. So if I show a relationship with somebody that you just met, you've only known for maybe a month or two, and you have kind of like a weak relationship or weak bond with them, are they going to have high potential? Like if you guys like aren't around each other anymore, or you get into a fight, are you going to have high potential for that relationship or that friendship to split up, or is it low potential? Who thinks that it's going to be low potential to change? Who thinks that they have high potential that they could split up? Good, very good. So if it's a weak connection, it's easier to break. And if it's easier to break, then that means it has high potential to cause a change. Because that's all potential energy is, or energy in general, the ability to cause change. Right? So here's a strong friendship. Maybe that best friend that you've had since kindergarten. So you are together, you have been through thick and thin, right? So is there high potential for this friendship to end, or is there low potential? Who thinks that there's going to be high potential to split? All right, who thinks it's going to be low potential? Very good. All right, so if you think of it in those terms, it usually helps. Because it's all about like what is normal, what's the original positioning, what would you expect to happen, right? So that takes us to slide 18. And so when humans and animals eat food, they store that energy within their chemical bonds, like the video on metabolism talked about. And it's to basically help maintain our cells, which, are the basic building block of our bodies. It also helps grow, helps repair, all of that business. And it provides us with the energy to move around. And so another thing that is kind of a nice side effect is that heat is produced as those bonds are broken. We all have an internal body temperature, right, that we have to maintain. If it drops too low, it can cause a lot of problems or even death, right? And so we don't always walk around bundled up, right? We have our own internal heat, and that comes from breaking of those bonds. So it's kind of a side effect that is very beneficial, but it is a side effect from these chemical bonds breaking, right? And so it's kind of important. We kind of talked about it before as well. If you're using an electronic device, like I think we talked about the PlayStations and maybe your phones can sometimes get really warm. If you have a laptop sitting on your lap, right, those internal parts are moving. Obviously, it's not your PlayStation's job to heat your room, but it does give off heat as all those internal parts are moving. So it's kind of a latent heat, we call it, or an unintended form of heat just because of the bonds that are breaking. There's also latent heat that's formed from friction, right? So if you want to warm up your hands, great, right? But in your car, you don't want your motor to overheat because those pistons are driving up and down in that motor, right, in that engine. So we use oils and things like that to try to keep friction lower. So sometimes, this is a good thing to have heat as kind of a byproduct. Sometimes, with certain moving things, we don't want that heat to build up and cause things to overheat and lock up. So, but in this case, it's a good side effect. Okay. I think I probably just ruined this, but that's okay. So what other benefits do chemical reactions in food give us? And again, sorry, spoiler alert. It's our ability to stay warm because of the thermal energy released during the digestion process as those chemical bonds are broken. So we will become experts on chemical bonds next year. All you need to think of with chemical bonds this year is that different elements come together and they form these bonds, and then when those bonds get broken, that's when energy and heat can get released. Right, and so we're keeping it very simple this year. So think of bonds as kind of that attraction between atoms. All right, so we're going to move on to our fourth form of potential energy, and that is electrical. And it was kind of introduced a little bit in the battery brain pop that we just watched as well. And so, again, we had this already, we just haven't talked about it in the form of potential energy. We already had electrical as one of our non-contact forces. So everything that you already knew is going to still be true. So this is a type of energy that is created when electrical charges build up, causing atoms to want to return to neutral. So again, what's it mean for something to have an electric charge? And we don't mean a full battery. What does an electric charge mean? And Kendall's the one that always answers this question. She's not here, so somebody else has to step up. Henry?
It has more protons than neutrons or electrons.
Okay, it has an uneven number of protons and electrons. Good. So maybe it has more protons, maybe it has more electrons. It could be either, they just can't be the same number. So you can't have 5 protons and 5 electrons, or 10 and 10. It has to be uneven. Remember the John Travoltage? The more uneven, the more electrons he gained. Didn't he become more and more charged? And then eventually, the more he built up those electrons, the more he wanted to like swing his arm and discharge into the doorknob. That's what you're supposed to be picturing right now, right? An uneven number. So building up those electrons, or possibly, it's easier to see the buildup of them. But it could also be the removing of electrons. So you're building up a positive charge. And so the farther away from neutral, which is like even, that you get that number, the more it wants to go back to normal. Just like the rubber band, right? The farther away from normal, the more it wants to get back to normal, right? And that's going to be the key here too. So quick reminder, we have protons. What charge do those have again? Charge are the protons. Let's see, Kellen?
Positive.
Okay. And then we have the neutrons. What charge are those going to be, Paul?
No.
Good, no charge. And then our electrons, Ronan?
Negative.
Very good. And then if we're talking positive and negative, it's going to be the protons and the electrons that are going to be the ones that are going to be affecting our electrical potential. Right? So normally, atoms contain they're kind of covered up, contain equal amounts of protons and electrons, so the charges cancel out, and it has no charge, meaning that the overall atom itself is neutral. That's the normal positioning. So just like my rubber band here, this is the normal positioning, right? No stretch to it. But if it has some kind of a change to it, then that's when it gains potential. And if we get this away from normal and we get a charge, that's when it wants to get back to normal and discharge. Okay. And so some atoms are going to hold their electrons more closely. So for example, your shoes, they hold their electrons closely, but the carpet does not. So when you walk, your shoes can steal or take some of those electrons and give your shoes a negative charge and leaving the carpet with a positive charge. We talked about, certainly now that winter is kind of here and we have the heat on, you're wearing sweatshirts more, and as you pull a sweatshirt off over your head, a lot of times, that will create that static cling or that static charge, and your hair will get all staticky, or you can even feel it, as you pull the sweatshirt off of you, you can feel that little tingle. You guys might have gotten that when we did the Van de Graaff generator. You could kind of feel that the electrons even in the air, just that little bit of difference from normal. So some other examples that we talked about before too were lightning, getting shocked, right? If you build up a charge and you touch something, you'll discharge, just like good old John Travoltage. that little simulation, the Van de Graaff generator, and then obviously staticky hair. Right, all of those things were lightning obviously being a huge static shock, staticky hair or just shocking someone is just a small buildup. But lightning is an extreme version of it, right, with the rumbling and tumbling of those molecules up in the clouds, building up that charge and then eventually discharging in the form of that lightning strike. Okay, so all of this is pretty much not new information. What we're going to do now is add in the potential part. So the bigger the charge, the more electrical potential an object has. And again, it's following our theme. The more it is away from its normal, the more it wants to get back to normal. So you can think of it like this. The more charge it has, the more it wants to change and return to normal. Just like our elastic, right? It's real easy to see. This is normal. This is something being done to it or not normal, so it wants to get back to this. And so if you keep in mind that the normal situation is neutral, if something's charged, it wants to get back to neutral. And again, you're probably going to get sick of me saying this, but all of this is a fantastic foundation for next year in physical science, because we're going to talk all about these elements and how they start out neutral. That is their natural state. All right, so the farther away from a neutral charge that an object has, the more it wants to return to neutral. And that means it has high potential to change back to neutral, meaning it has high electrical potential energy. And again, this is common sense. If you think about it reasonably and logically, there's nothing to memorize. Just think about what is happening and it should make sense. Because if an object has a neutral charge, all you have to do is ask yourself, what is an item normally? Well, it's neutral. And if it is neutral, then it doesn't want to change. It doesn't want to gain those electrons. So it has low potential to change and become charged, meaning it has low electrical potential energy. Okay, so pretty straightforward. It's just trying not to memorize it, trying to think about it logically is the better way. Okay, so if it's charged and the farther from neutral it gets, the more it wants to discharge and get back to normal, so it has high potential to change. If it's already the way it wants to be, then it has low potential. Okay? All right. Let's take a look. Back to magnetic. So gravitational, electrical, and magnetic, those were our three non-contact forces. And so again, we've already talked about the first two, and here's our third one. The magnetic potential energy that something has. So this is a type of potential energy based on position, and it depends on the attraction and repulsion of the north and south poles within those invisible magnetic fields. So obviously we're seeing the field lines as you leave the north and go into the south. You can follow the direction of those arrows, kind of working along the same lines as the positive and negative end of a battery as you flow out of the one and into the other. It's kind of that same idea. They're both involving that relationship with the electrons, which is why you can temporarily magnetize a non-magnetic item if you put an electric current through it. And so for all these, we're assuming that the magnets are within the magnetic field. So right now, my magnets here are definitely in the same magnetic field, right? If I push them too far away, they're out of the field. So for all of these examples that we're gonna look at, you can assume that they are close enough that they're gonna do what they're gonna do if you let them, okay? All right, so let's take a look. We have to look at what the normal positioning and everything is. So all magnets have magnetic poles. They have a north and a south. Okay, and so what will a north and a north pole typically want to do? Andrew? Okay, so they're going to repel. What are a south and a south going to do? Let's see, who haven't I heard from? What do you think, Ads?
Repel.
They're going to repel. And then what are a north and a south going to do? What do you think, Isaac? They should attract. Okay, and you can see that here if you want to cheat a little bit, right? There is the opposites attracting, and the like charges are repelling. Okay? All right, so if you keep that in mind, those are the normal positions. So anything other than that, it's going to want to get away from that, right? It's going to want to get back to that. So keep in mind the way they normally react, that's the normal, that's the original. Just like this is the normal and the original. Okay, so we talked about electromagnets, we talked about compasses using this, Earth's magnetic field. All of these have some form of magnetism, and so they should have potential energy with them as well. Sorry, might have gone too fast. So it's kind of a nice little review from our first unit, here about a month later. Just kind of reinforce that. Okay, so just like with elastic potential energy, when objects or magnets, in this case, are far from their natural position, the more they want to return to their natural position, which you see here. Opposites are attracted, these two are repelling, likes repelling, right? So those are all showing their normal positioning, so they are happy the way they are. And so this is opposites attracting and likes repelling. And so the more they want to return to normal, the more potential they have to move. And that means the more magnetic potential they have. So if you would move them away from their normal, that's when they want to have high potential, or that's when they do have high potential to get back to this. So if I'm holding a north and a south, they're here together. If I pull them apart, but they're still within the field, right? Now, obviously, if I move them like this, they're out of the field, so they're not going to attract. But if I have them in the field and I just separate them a little bit, they want to go right back. And you can hear that click, right? That's the way they want to get. Or if I take a south and a south, when you were getting to play with these, you could get them to move, right? Because I'm pushing a south and a south away. And we'll get a chance to kind of play with these again a little bit. So you're able to push it away. But if I'm holding a south and a south together, is that the way they want to be? No. So if I let go, what are the magnets going to do? They're going to want to return to normal, which is away, right? So they push away. Same thing with the north and the north. If I'm holding them kind of against their will, they're going to push away. Okay, so we will, let's go ahead and stop there. And we will pick up tomorrow. And remember, we have a 2-hour early release tomorrow. But we should have time to finish the notes and then maybe even get to some